Welcome everyone. In this video, we will talk about projections. So first I'll explain what is a projection, give you some notations, and then we'll do an example on how to find vector projection. Let's take a look at an illustration. Let's suppose we have two vectors. So let's call this a vector v, and let's call this vector right here vector u. So what you want to do here is to project this vector u onto v. So the way we're going to denote that is by using the following notation. So we want to know what is the projection of vector u onto v. So the one you're projecting onto is written as a subscript like that. Now, what is this? Well, this is going to be a vector. Now, since it's a vector, we know vector will have a magnitude and direction. So these are the two things we need to find of this particular projected vector. Now let's take a look at how we're going to project this onto vector v. So imagine you put to look at its reflection or its shadow right over here. So think of it as it goes down onto this vector and you're creating this vector. This is shadow of the vector u onto v. And that's what you want to find. So this vector right here is what we call the projection of u onto v. I hope that illustration makes sense. Now, how do we find this vector? Well, we know that vector has magnitude and direction. Now, I forgot to show this is a 90-degree angle right here. So how do we find the magnitude of this projected vector? So the magnitude is going to be called the scalar projection. In other words, this length right here, this is what we're going to call the magnitude of this vector. Now, the magnitude of this vector is component of the vector u onto v. So that will be the magnitude of this vector. Now, let's see how do we find that? Because once we have that, then we just simply plug that in here. And then the next thing we will need is just the direction. Okay, so let's see how we get this. So I'm going to go ahead and pull this right triangle out. As you can see it, it's right in space. So imagine the triangle, it looks like this. So this is the triangle we're looking at. So it's a right triangle. And let's say we also know theta. So let's say theta is located right here. That's between the two vectors u and v. So theta is right here. And do we know this length right here? Well, yes, that's the magnitude of vector u. So let's call this the magnitude of vector u. And we want to know what this length is. So let's call that x, because that's what we're looking for. That's the magnitude of this projection vector u onto v. So using our trigonometric ratio, we know cosine of theta is going to be adjacent over hypotenuse. So this is adjacent, this is hypotenuse of theta. This would be x over the magnitude of vector u. And then if you solve for x, because that's eventually what we're looking for, this length x, it's going to be magnitude of vector u times cosine theta. Now, if you don't know theta between the two vectors, then this formula becomes a little bit of work. So what we're going to do, we're going to multiply by 1. And 1, we're going to write it this way. We're going to multiply this by magnitude of vector v divided by magnitude of vector v. So that's the vector you're projecting u onto. And now if you formulate this, rearrange the terms, this is really magnitude of u times the magnitude of vector v times cosine theta divided by the magnitude of vector v. Now, if you recall, this is our definition for dot product between the two vectors u and v. So we can rewrite this as u dot v divided by the magnitude of v. So this is what we're going to call the component of u onto v. So that will be the magnitude of this vector projection. And this is really a good way to rewrite the vector we initially wanted. So let's go ahead and plug this in up here into our magnitude right here. So we know projection of vector u onto v is going to be magnitude times direction. So the magnitude, we just got it. That's the component vector. I'm going to go ahead and replace that right here. So this will be component of vector u onto v times, now we need a direction. Well, we're going to be going in this direction, in the direction of vector v. So we're going to make that into a unit vector. So we're going to multiply this by vector v divided by its magnitude. So there you have it. That's how you find projection of u onto v. Now you can reformulate this. For example, this piece right here, you can write it in terms of the dot product of the two vectors. So I'm going to rewrite this for you again. So we can say that this can also be written as u dot v divided by the magnitude of vector v. And of course, we still carry out v over the magnitude of v. And if you want to simplify it further, so this is also another way to write the same thing. Like if you want to write it further, simplification of this formula. So these two can be combined together by using exponent. So this is simply u dot v divided by the magnitude of v squared times vector v. Now put parentheses around so that you know you have a vector eventually. So this will be another way to write the projection of u onto v. Let's try this example. So we want to find the vector projection of u onto v. So just like the way we derived last time, we're going to use that formula. So we know the projection vector of u onto v is simply the component projection of u onto v, which is the magnitude of that projected vector, times the unit vector in the direction of v. So this will be vector v divided by the magnitude of v. Now, if you want to picture this, so you'll see how the formula can change in the future. So here's your vector v, and here's vector u, and we're going to project u onto v. So we want to find this vector right here. So this is the vector we're looking for, this one. This is what we want, because this is the projection of u onto v. So we know v has components. Let's write them next to each vectors. So v has the component, so it's given in terms of the standard unit vectors. So k, which means I and j are 0. So v is written as 0, 0, 1. And u, again, it has its I component as 6. So that's 6, j is 9, and k is 2. So these are the components of these vectors. And now we're going to find the component projection of u onto v, which is u onto v can be written as, this is u dot v divided by the magnitude of v. So u dot v, so we're going to use the dot product. So u is, so 692. So we're going to multiply these corresponding components and add them up. So we get 6 times 0, that's 0. And the 9 times 0, that's 0. 2 times 1, that's 2. Divided by the magnitude of v. So that will be the square root of 0 squared plus 0 squared plus 1, which is 1. So we know this component, it's going to be 2 over 1, or simply 2. So we know the component of u onto v, or the magnitude of this vector, is 2. So that's what we're going to replace right here, 2. Now we need to find the unit vector in the direction of v. So v divided by its magnitude, it's going to be, so v has the component 0, 0, 1. So we have 0, 0, 1, and its magnitude is of course 1. So this vector is just 0, 0, 1. So that's the direction of our new vector. So now we plug this in here. So we have 0, 0, 1. And then if you simply multiply the scalar 2 with its magnitude, you'll have your vector projection. So this will simply be the vector 0, 0, 2. So that's our vector projection of u onto